Rotating detonation engines, RDEs, represent a significant innovation in propulsion technology, promising higher efficiency and performance compared to traditional engines. Unlike conventional engines that rely on deflagration, subsonic combustion, RDEs utilize continuous detonation waves, which propagate around an annular combustion chamber. This method leverages the higher pressures and temperatures generated by detonation, leading to substantial improvements in fuel efficiency and thrust. The core principle of RDEs is the continuous detonation process. In an RDE, a detonation wave is initiated and sustained within an annular combustion chamber. As the wave travels around the chamber, it compresses and ignites the incoming fuel-air mixture, creating a continuous and self-sustaining detonation. This process produces higher pressures and temperatures than traditional combustion, resulting in more efficient energy conversion. RDE comprises several key components, including the combustion chamber, fuel injectors, and the detonation wave initiator. The annular combustion chamber is designed to facilitate the continuous circulation of the detonation wave. Fuel injectors introduce the fuel-air mixture into the chamber, while the initiator ensures the detonation wave is sustained. RDEs offer several advantages over traditional propulsion systems. The use of detonation waves, which propagate at supersonic speeds, results in higher thermal efficiency. This leads to improved fuel efficiency and reduced fuel consumption. Additionally, RDEs have the potential for a higher specific impulse and thrust-to-weight ratio, making them suitable for applications requiring powerful and efficient propulsion. Despite their potential, RDEs face several technical challenges. Achieving stable and continuous detonation is a primary concern, as fluctuations in the detonation wave can lead to performance instability. Material durability is another critical issue, as the high pressures and temperatures generated by detonation require materials that can withstand extreme conditions. Noise and vibration associated with continuous detonation also pose significant challenges, necessitating innovative solutions for practical implementation. The unique characteristics of RDEs make them suitable for a range of applications. In aerospace, RDEs could be used in rockets and hypersonic aircraft, providing the high efficiency and thrust needed for space exploration and high-speed flight. Military applications such as missiles and other defense systems could also benefit from the enhanced performance of RDEs. The ongoing research and development in this field highlight the potential for future breakthroughs and practical applications. Several organizations and institutions are actively working on RDE technology. Recent breakthroughs include successful experimental demonstrations of stable detonation waves and improved engine designs. Key players in this field include leading aerospace companies and research institutions, which are making significant strides toward realizing the potential of RDEs. Future goals include achieving longer operational durations and integrating RDEs into practical propulsion systems. Comparing RDEs with conventional jet engines and rocket engines highlights their unique advantages. Traditional engines rely on subsonic combustion, which limits their thermal efficiency and specific impulse. In contrast, the supersonic detonation waves in RDEs enable higher efficiency and performance.